So welcome back, everybody. I hope you had a great start for the week and a good weekend as well. So I just wanted to give you quickly the basic messages for what we are going to go through this week and a little bit about the plans. And so let me just quickly go through that and remind you of some practicalities as well. So if we look at this week here, what we're going to do now is actually to revisit things which you've seen before. And last week, we actually started to look at this falling object in one dimension. And I hope you don't get offended if we play around a little bit with that, because that's going to allow us to catch many birds with just one stone. We are going to look at applications of Newton's laws, but we will also try to link this with the specific way by which we solve the equations. And we are going to scratch the surface of us starting to think of writing a program which implements Newton's laws. And this kind of program is something you will use again and again and again. So it's going to be a mix of paper and pencil calculations and start getting to look at the numerics. Now on Friday, depending on how far we end today, we are going to use 15 minutes roughly, 20 perhaps, of the lecture and just trying to wrap up the theory. And then we have the rest of the time for solving the exercises. Now, as you've probably seen, the second exercise set is also available. So if you want to dive into that one and you're done with the first one, feel free to bring that up as well on Friday. But we, as you probably see now, the deadline is actually not this Friday for the second assignment. That's the Friday thereafter. And you will typically find these assignments roughly 10 to 12 days before the deadlines. So that's going to be the kind of way we put these up online during the whole semester. Now, I just wanted to quickly remind you of a small practicality before we move on. And just a quick update about office hours. So if you go back to the main GitHub website, if you scroll down, you will find, again, just to remind you, we have this room. I don't think there is anyone after 4 o'clock here. So if you wish to hang around on Wednesdays, as well as on Fridays for solving the exercises, feel free to do that. So I tend to have office hours right after that. So feel free to hang around if you can. The Shuju has office hours on Thursday, as you can see here, from 1 to 2. So that fits well when you're solving exercises. And since we have the deadlines on Fridays, and you probably notice that on D2L, we put the deadline on, actually, we keep it open till Sunday, that just in case something happens. But it's good for your own planning, just to think of being done on Friday, so you don't have something hanging over during the weekend. And then Abby has office hours in BPS, so you can reach out to Abby in BPS every Thursday. And I have an additional office hour on Tuesdays from 8 to 9 o'clock in the evening. So if you're feeling lonely in the evening, you can just jump into the Zoom session and then we can chat about exercises or whatever you want. Okay, so let me go back to, I'm going to use the slides a little bit in the beginning, and then we are going to go back to the whiteboard and remind ourselves a little bit of what we did last week. One thing you will also find every week, you're going to get this email with some reading recommendations. But what we are going to look at now is some of the basic steps of a scientific investigation. And as I mentioned in the beginning, we want you to start thinking as physicists or scientists. And one of the things which becomes very useful for us then is actually to identify and set up a problem. So in the second exercise set, you will see some cases where we are triggering your intuition and just to set up the forces which act on the system and so on. So this is essentially what these few slides are about. And this kind of steps are the typical steps which we always end up doing when we do science, whether this is mechanics or quantum mechanics or electromagnetism, etc., etc. So in this course here, we are going to deal mainly with the point objects. So that means that when you have a ball, that is something where we leave out internal forces between the atoms and the molecules in the ball. So the ball is to be considered as a point object. When we are going to write a program about the solar system, all the planets are going to be treated as point objects. So that's one of the basic approximations which we make here. So you have to identify the system and ask yourself what kind of object is moving. What kind of data do we have, in case you have data about it? How do we measure position? That's a very common type of measurement, velocity, acceleration. Which initial conditions influence the system? And one of the things you're going to see is that basically all the systems we have, when we have solved the equations on paper and pencil or numerically, what is going to define the system are actually the initial conditions. So classical mechanics, as we're going to be doing in physics 321, is a set of, is normally rephrased in terms of differential equations where we define the initial conditions. Sometimes we end up with the boundary conditions. So if you have a beam or a spring which is fastened in both ends, that's a boundary condition. And that leads normally to partial differential equations. We will mainly stay with ordinary differential equations. And you also need to look at other aspects which allows us to identify the system. And if we move on, the other things which we need to think of when we are dealing with a specific physics systems is that we have to define a model. And we have to find the forces that act on the system. That was actually a big debate before, and it's still a debate. What do we actually mean by the forces? And there are many small philosophical discussions. Sometimes I bring in this kind of philosophical aspects because when we do physics, that is tightly linked with the philosophical interpretations of what we do. And you will see that when you go back to Newton's, when Newton presented the Principia, there was a big debate on action at distance when Newton presented the gravitational force. And many people actually contested that point of view. So if you're interested in the philosophy of physics, there is a lot of interesting discussions which went on and still go on about that. But we have to find the forces that act on the system, and then we have to make models for the forces. Now, we do have some fundamental forces which we can play with in classical mechanics. It could be the Coulomb force between two charges. It could be the gravitational force. But you will probably be surprised to know that a force like friction is something which we don't have a fundamental force for. Friction is often rephrased in terms of some effective model. So one of the cases we are going to look at when we look at this falling object is whether this object is falling in fast way or whether it's falling slowly. And then the air resistance may actually be modeled in different ways. So this is again something which we have to live with. And in other cases, we may also have effective forces because we cannot, the problem is so complicated that we end up with some kind of effective force between the objects. So we need to do that. So there will be some kind of modeling. So we have to deal with models. We have to identify the equations which govern the system. In our case, the equations are going to be Newton's second law. These are the equations which we will start with. And when you have other elements which you may deem important for defining the model. So in some of these exercises we have this next week, you will actually have to do this. So the other things which we need to think of when we are solving exercises and analyzing a system, now we need to solve the equations. And in our case, typically what we end up doing is to solve Newton's law. You need to define the initial conditions. And then the solution gives us then the position, the velocity, and other time-dependent quantities, which you can actually link up with the experiment, if you have experimental data. And then when you've done that, that is when you analyze. So now it's time when you can ask questions. What do the results mean? Do they agree with what we expected? Are they correct? So if you think you have done things correctly, is your position as a function of time reasonable? Do you trust what you did? And can you validate and verify the correctness of your results? You need to evaluate the answers and the implications and compare with experimental data if it's possible. So coming again back to the simulation of the solar system. So one of the things you're going to do is actually to write a code in the second midterm for that. And last year, we had a vote whether people wanted to do that. It sounded, as I said last week, a little bit difficult, but actually everybody ended up doing that. And it's a great satisfaction. And clearly when you simulate the solar system, if you get a solar system which is unstable, that does not agree with experiment, right? Or observations. So that would be a typical example of your simulations not giving the correct results. So suppose Mars leaves its orbit, then most likely we have done something wrong in the simulation. And then clearly all these elements bring us back to the first stage. It may happen that the data are not good enough. It may happen that the equations and the model which we developed was not reasonable or was not a good model. And then this kind of questioning is actually what defines all the essential elements in scientific inquiry. So with you developing the numerical tools together with paper and pencil, the whole hope is that you can develop this kind of intuition about physical systems and be able to assess whether the model you have is a good one or not. So the gravitational force, which was introduced by Newton, agrees with experimental observations. And this has been tested over and over again for 400 years. And it seems to be something which we would call a fundamental law. So the next steps, which we just need to remind ourselves a little bit about, is Newton's law. So I'm just leaving this here. But I'm going to repeat some of these things. When we are going to analyze a system, we need to analyze whether we have long-range forces or contact forces. So these are the typical forces which we will distinguish between. So the forces are either going to be long-range or of the type of contact forces. So if you think of a contact force, what comes to your mind as a typical example when we say a contact force? Any good suggestions? Yeah? Friction. So you have a block sliding on a plane, and friction is one of the classical examples of a contact force. If we think of long-range forces, what is one of the obvious ones? So gravity. Excellent. Excellent. So we're also going, as I said, to look at point particles. And we typically distinguish between the object we are studying and how this system interacts with the environment. And we can distinguish between isolated systems. So when you're thinking of the solar system, you could actually think of that as an isolated system of the different planets. And then you have the forces between the planets, and that is your system. On the other hand, you can have an object which is sliding on a plane. So the object could be a block which is sliding on the plane, and the environment would then be defined by the plane, which is in contact with your object. This is a kind of analysis which we are going to do again and again throughout this semester here. And as you can see here, if you think of a force of a falling object, that must be related to an interaction with something in the environment. And that means also that we do not consider internal forces. So if you look at this block, which is sliding on a plane, not the most exciting problem anyway, we are never going to study the internal forces which keep the block together. So the block is just going to be one object. And the internal forces, that becomes more the topic for thermal physics, statistical physics, and obviously quantum mechanics. And we are not going to dive into that level of kind of say depth of physical phenomena. So a quick reminder of setting up the model. And I'm actually going to switch over to the whiteboard just to remind you of these basic steps. But you will find many of these basic steps here. So we're going to divide the problem into system and environment. You have to draw a figure of the object and everything in contact with it. You draw a closed curve, or you make a figure of the whole system. And then you find the contact points. You give names and symbol to all the contact forces. And this is actually what you're going to do in the next assignment. There are some simple problems like a falling object and find out which are the forces. And you need to identify the contact forces, the long range forces, and then you make a drawing of the objects and find all the forces. And then when you find all the forces, then you have the acceleration, which acts on the specific object. And when you have the acceleration, then you can start calculating. Okay? So this is a kind of overarching view on what we are going to do again and again in this semester. The only thing which is going to change is actually the kind of physical system you're going to look at. But you identifying the forces is actually the first step, which will lead us to the heaven of physical systems and solutions and deeper physics insights. So let me go back to the whiteboard so we can rewrite what's on the slide here in a different way. Just as a quick reminder, you've seen this expression here. So I hope I'm not repeating too much, but the first 2 to 3 weeks, we're going to repeat a little bit. And we have Newton's first law. And just to quickly remind you of that, the Newton's first law simply states that, well, you can actually read through what we have in the slides here, actually. So I'm going to let you read through that and rather switch over to the whiteboard. So take a look at the slides here, because this is just a quick reminder on the 3 laws of Newton, which we are going to use repeatedly. So let me just switch back to the whiteboard. So if we look at these basic points of the kind of analysis which we need to make when we are dissecting a physics problem, so what we typically will end up with now is the following. So we have some definitions when we are analyzing a physics problem. So let's just write this down. Analyzing. So in this case, it's actually a mechanics problem, but let's call it a physics problem because it's pretty generic actually. So one thing which we have are inertial masses. That's probably a word you've seen in different contexts. So an inertial mass is actually determined by measuring the acceleration for a given applied force on an object. So we are going to assume that the objects which we have, the masses which come from an object, they are determined by measuring the acceleration which we get by applying a force on a specific object. By measuring the acceleration for a given object or for a given applied force on an object. So we know what the force is, we measure the acceleration, so then we can extract the inertial mass. So this is just given by Newton's second law. And then there's another important property of these inertial masses, that is that they are additive. And we are going to make another assumption in most of the applications. And this is an assumption we make. They are time independent. So that means that the masses in most of the problems we are going to look at, they are not going to change their mass. If you're thinking of 2 colliding particles which fuse into another one, they lose energy and they will also change mass. These kind of processes are processes which we will not deal that much with. So most of the objects we are going to look at, they will have a mass which is time independent. So it stays the same over time. So this is another assumption which we are making. So the inertial masses are additive, and we are going to assume that they are time independent. So which means that if we do the derivative of the mass, dm dt, this is going to be equal to 0. That's in most cases. So they are additive, which means that the mass of the system is given by the mass of object 1 plus object 2 up to some mass of object n. And this is then given by a sum from I equal 1 and up to n. And then we have an m of I here. And that means that the final force which acts on the system, so that means that the force now is going to be given by m times the acceleration here. So when we are setting up a system. Now, when we now want to analyze a system, we are going to assume that we are dealing with point particles. Point particles. We are not going to look at the extension of an object. And when we now analyze the problem, we are now going to analyzing a given problem. We are going to follow the following steps, which were also in the slides. We are going to divide. So let's set this up. So we divide the system into, divide into system, which we want to study, and environment. In many cases, we deal with what we call isolated systems, and that means that we neglect the effect of the environment. So we are coming back to that. And we assume also that all forces must have a source. So these are some basic assumptions which we are going to make when we now make a model for the type of physical system which we are going to be at play in the system here. So they must have a source when they act on the system. Then one of the other things which we have is that forces are either long-range forces or either long-range forces or contact forces. And as I mentioned, we do not consider internal forces. So when you define an object, we disregard all kinds of forces which are at play between the atoms or the molecules which make up this specific object. So it's just the object. Okay, so these are the kind of assumptions which we make. So this will be the first part. So let's call this one part 1. And then we can go down to part 2 here. And the first simple thing which we will do now is just to draw a figure. And you're going to see how to do that in the next exercise. So draw a figure of the object. And everything in contact with it. And everything. I should say it's not only one object, it can be many objects, and everything in contact with it. Then we make in the next step, we make a graph or make a sketch of the system. We find eventual contact points in order to define contact forces. Find contact points. And then name all forces. That was the next thing. Name all forces, which we can identify. And then we need to identify long-range forces and contact forces. Long range and contact forces. And then comes another thing which we have to define, and that's actually to decide upon the type of coordinate system which we want to deal with. Decide upon choice of coordinate system. And the one which falls very intuitive for most of us is actually the standard Cartesian coordinate system. So these are some of the basic steps which we need to set up. And normally we just have all these kind of basic steps. Most of you have already done this kind of reasoning, but I just wanted to remind you of it because that's the kind of approach which we use when we are going to dissect a physics problem. And a typical example, if we now take a closer look at it, could be a ball which is rolling on a plane. So suppose we have a plane here, and then we have a ball. You can see my drawing skills are not optimal, but just imagine this is a ball. Let's pretend. And we have a mass center here. So we would typically now draw the gravitational force. And as you all said just some few moments ago, this is a long range force. And then if you now look at what we could have, so we could have a force from the ground, N from the plane here. So let's put vectors on it. So normally what's called a normal force. We could have a force from the floor on the ball, which is due to friction. So we could have some force which acts on it. So let's just put it up like this. Some Fd. And this could be some kind of friction force, which we have left unspecified. There can be other forces at play here. So let me just write it like this on F of B. So this is normally called a buoyancy. I don't know if I pronounced that correctly. So which is attributed to different air pressures. Now you can have some air resistance, which is the difference in velocity between the surface of the ball and air, and so on. Often we would simplify things, and sometimes we don't have a clear model for it. So if you think of friction, this is actually some of the things which disappoint many people, that we don't have a clear, nice, well-established closed form expression like we have for gravity. In gravity, we have something which depends on the inverse distance between the objects squared. Whereas for friction, this is something which is left to modeling. And people use, I don't know if you're familiar with it, in solid state physics and condensed matter physics and material science, there is a mathematical tool which is called molecular dynamics, where you actually try to extract phenomenological forces between atoms, and then you would simulate the motion of a ball in its contact with a surface in terms of this more atomistic approaches, but using Newton's equation and no quantum mechanics. And then you would solve equations for billions of particles which interact with each other. You would have the surface of the ball and the surface of the plane, and then look at the interactions between the atoms in the ball and the atoms on the surface. And then you can model friction. This is actually current research in material science, and it's actually hot field and a big field in applied material science and condensed matter physics. And the mathematical tool is called molecular dynamics. So if you're interested in this kind of research, I mean, just let me know and I can direct you to the right people who do that. But this would be a typical example of a system. And when we have the forces, then we sum them up, and then we have the total force acting on this specific object. And that allows us to define the acceleration. So let's do that. So when we have done this, what we want to do then is to define what we would call as the net external force, which is now acting on the object. So just gonna call this an F net external force. So that's going to be given by the mass of the object times its acceleration. And we would have the gravitational force, we have the standard normal force, we have this friction term, and then we have this term FB. And then we can obviously have more complicated forces which we add. So the forces are additive. So we're actually looking at the superposition, and the acceleration due to many of the forces is the same as the acceleration of one force equal to the sum of all the different forces. And Newton's law, as we said, is going to apply to this kind of point particles. I hope this was not too boring. Now I wanted to go back to the system which we had last week, which was this simple ball which was falling in one dimension. And then we're going to add air resistance to that. But before we do that, we are going to look at two strategies for solving the problem. So what we had last week, so if we can now go back, by the way, any questions to what we went through now? So this is things, I wanted to bring this up just to have us start thinking about the basic way we dissect a physics problem. And then, yeah. Say it again. So in the air resistance here is something you could include now in one of these additional forces here. So I didn't put it in that model. But some people would actually think of air resistance and frictions among much of the same lines, because you would look at the different pressure which the ball is experiencing and the air is experiencing, or the velocities of the ball and the velocity of air. So this FD could contain both the friction from the plane and from air resistance. So that's a good question. Yeah. Say it again. Oh, you could actually, in this case, you could actually put the friction against the ball. Yeah. So I just put it up here just to. I wasn't very precise here. You could think of friction as something which acts against the ball, but then I would have to introduce two dimensions. So right now, I just wanted to stay in one dimension. Okay. So as soon as you have two dimensions, you would have to think of friction as something which could go in the x-axis against the ball, and then you could have some air resistance which acted both in the x direction and in the y direction. So here, I just forgot to say that I opted for a coordinate system, which is one-dimensional. Okay, so you also have, this is one of the choices you have to make when you start analyzing a physics systems, whether you are dealing with 2 dimensions or 3 dimensions, a Cartesian system, or if it's more handy to switch to spherical coordinates or polar coordinates. So these are things which we're going to see a little bit later when we move on here. Yeah, sorry for forgetting that about the one-dimensional thing. So let's now look at the falling object, which we looked at last week. And in that case, we had a very simple case. So we had minus g, and we had minus m times g. And I'm going to take away vectors because I'm going to confine this to one dimension, which means that the force now, I don't need to define a specific direction. So the g is no longer a vector. And the acceleration is given by m times g by the gravitational constant. And then what we did when we rewrite this equation here, this is the same as m times the derivative of y dt, second derivative. And we would typically split this when we are solving the equation into two first order differential equations. So we would have one equation for the velocity, which is given by the derivative of y with respect to time. And then we would have the acceleration, which is given by dv ddt. Okay? So these are the two equations which we would typically solve. And I said that we would have, typically in this course, we're going to look at two approaches to solving this problem. One, if we can integrate analytically, we should do that. But in many, many cases, we don't have an analytical solution to the problem. And then we have to apply numerical solution. But any type of solution which we are going to, any solution strategy involves integration. Because you look now, if you look at the equations, you have the derivatives. If you want the velocity, you have to integrate up the acceleration. If you want the position, you have to integrate up the velocity, okay? So let me just quickly remind you of what we did. And then we are going to jump into the other approach, which is the numerical approach, which we are going to use throughout this semester in solving the equations. So the first approach now, if you now look at the equations, is to define, we will always do that, define initial conditions. Because you're going to have a myriad of solutions. And if you specify the initial conditions, then you're going to have a unique solution. Because your solution will be a general one, but it's when you specify the initial conditions that you will get the unique one for the system you are studying. So you would typically specify a V at time t0, which we last week dubbed as a V0. And then we would also specify the position at t0, and time is given by the variable t. And t0 is something we are going to use throughout the semester to indicate that this is the initial time. And if we now look at the equations here, when we now integrate up from a time t0 to a final time, and we take the acceleration of dt, this is going to give us t0 up to t of dv, this is going to, let me just rewrite this. So in this specific case, this is now going to be equal to t0 of t of dv dt prime of dt. Now, this one, when we integrate it up, is going to be given by v of t minus v of t0. And in this particular case, the acceleration is just given by the gravitational constant, which means that we get this one to be equal to t0 of t of minus g multiplied with dt prime. And that gives us minus g, and then I have the final time minus t0. And then depending on initial conditions, and it's pretty common to put t0 equal to 0. So in that case, it means that we get, with this, we get a v of t is equal to this v0 minus g times t. So this is the standard approach, which you probably have seen many, many times. Is this integration step, is that okay? Everybody's familiar with the mathematics here? And then when we've done that, we would go back to the expression for the velocity in terms of the derivative of the position. And we would then repeat this calculation. And we will take now the integral from t0 to t. And then we would have our v0 minus g times t. And then we would integrate this up to a given time t. And this is going to give us y of t minus y of t0. And we can choose, in order to simplify things, we could now choose v0 equal to 0. You could think of u starting with an object, which is at rest, and then you just let it fall. That's a typical initial condition which we can choose. I do this because I'm notoriously lazy, and it makes the mathematics much easier. So when we integrate up, what we get then is minus 1/2 of g times t squared, and this is equal to y of t minus y0. And then we reshuffle a little bit. So we find that y as a function of t is given by this initial position minus a 1/2 times g of t squared. So this is an expression which we now are going to modify. But this is the first approach for solving the problem. So if you can integrate up, if you can do that analytically by paper and pencil, I mean, setting up a program is a kind of overkill. However, when you write your first program, this is a very useful test that your program is running correctly, because you have an analytical expression to compare with. So if you have that, that is a gem, because then you can always, if you're in doubt whether your program is going correctly or not, you can always check that with the analytical solution here. So let's now look at the second approach, which is the numerical approach. And this is the numerical one. And I'm going to give you some of the basic steps which we would typically use when we are doing that. So in the numerical approach, we would also start with writing the equation in terms of two first-order equations. So we would have dt, the derivative of velocity, which is equal to acceleration, and dy dt is equal to the velocity here. So these are coupled differential equations which we are solving. And when we are integrating it up, the basic recipe we're actually going to do now is to use a Taylor expansion. So this was also one of the reasons why we have a Taylor expansion in one of the first exercises, just to remind you of that. So what we are going to do now is to Taylor expand the position, for instance, around a variable delta t. So this is a step size, which we are going to define. And this is when we Taylor expand it, we know we have a famous expansion here, y of t plus this delta of t multiplied with the derivative of y of t. And then we have higher order terms, delta t squared divided by 2 factorial. And then we have the second derivative. And now I'm going to write this in terms of the higher derivatives, but just putting a delta t cubed here. What we can do next now is to rewrite this equation here, and we will typically truncate, assuming that delta t is small, and also that higher derivatives are less important, and truncate at first order in delta t. At delta t. So that means that we are going to get an expression now for y of t plus delta t, where we can put an approximation sign. And this is given by y of t plus delta t times the derivative of y of t. Have you seen this before? It's going to lead to an approximation which is named after a famous mathematician. Anyone remembers that? Yeah? Euler. So this is going to lead to Euler's forward method. And this is the simplest method which we can implement numerically. Okay. So what we are going to get then is, when we now rewrite it, because we discretize, so t is going over to t of I at a given time step, and that's going to be given by times t0 plus I plus this delta t. And then I'm going to rewrite t plus delta t as y of I plus 1. We just move one step. Y of t is going to be given by y of I. Now, if you look at the expression here for the first derivative, what is that? Can we replace that y derivative with some expression? So let me just scroll up again and see if I can help you. So if you look at the y of t here, the derivative, if you now look back at the original equations, what can we replace that derivative with? Yeah, the velocity. Thanks. So we can rewrite this equation now, but we don't have the velocity. This is actually one of the unknowns. So we can rewrite this equation, y of I plus 1. And now I'm going to put an equality sign. I'm going to be sloppy. And this is going to be given by y of I plus this step size, delta t, multiplied with v of I. That's the first equation. This is the way we are going to replace the integration which you saw here. This integration, we are going to replace that one with this stepping equations here, where we now integrate from the initial time to the final time. So this is the second approach. And now we do the same with velocity. So we take v of t plus delta t, and that's given by v of t. And now we do the same truncation. We can do the same Taylor expansion, and we have delta t of v of t. It's actually an approximation because we've taken away higher terms in delta t. If you now look back at the expressions you have here, what can I replace the derivative of v with? Acceleration. So what we have now is two coupled differential equations, which we would start solving. So the equation which you can frame in and put on your bedpost before you go to sleep, because these are some of the first equations which we are going to implement, is delta t times v of I. And then we have v of I plus 1 is equal to v of I plus delta t multiplied with the acceleration. So we are going to make an algorithm here also where we define delta t, which is going to be given by the final time, tn, minus the initial time, divided by the number of discrete steps we make. So it means that delta t is a known quantity. Now, and this is where we go back to where we began today. So if you have done the analysis of the physics systems which you have, and we have specified the initial time and the final time, so it means that this is a known quantity, and we specify y0 and v0. So these are the initial conditions. So everything here is known. So your final time is something you decide upon. The initial time is something you define. Delta t is something you define. You define the initial conditions. Now, what is known in this equation, two equations now? What do we have as a known quantity besides the initial conditions? Yeah, or the acceleration, right? If that's gravity. So the known quantity, when we have done the analysis of the physics, we know the acceleration. And when we know the acceleration and the initial conditions, we can solve these equations. So what you see here is actually the discretized version of approach 1, where we integrate it. Now, for this simple case with a falling object, we can integrate easily. There's no problem in ramping up a numerical exercise here. But we are going to, when we add air resistance to this problem, you're going to see that we cannot integrate analytically. And then we have to solve numerically. So even for a simple expression for air resistance, we cannot integrate this analytically. And we have to do it numerically. And that's going to be the numerical exercise in homework number 3. But now we just need to build up the basic mathematics and numerics here. Any questions? Is this too simple, or is it okay? So if our time is over, but if you wish to hang around and you have questions about the course or practicalities or whatever, feel free to stay around here. But now I'm going to switch off the recording here, okay? So to those of you online, all the best. I'm going to stop the recording, but if you have questions, feel free to do that.